Just okay, thank you for inviting me for this seminar. It's nice to be here, although virtually. I will start with short plan of my speech. First, I will say a bit, just a few words about singular optics group. Then a brief introduction to optical vortices. And next, optical vortices microscopy, ending with some conclusions. So singular optics group, and there is one small remark. I am from Wroclaw University of Technology. Wroclaw University is a separate unit, and locally here is an important distinction.
Mm-hmm.
Okay, singular optics group is with the chair of optics and photonics. Chair of optics and photonics split into 3 research groups: fiber optics group, singular optics group, and visual optics group. As you can see here, people working in my group, people with PhD degree or higher, are listed first. Then we have, unfortunately, only one PhD student now. This is not comfortable situation. Some PhD dissertations have been completed last year, and I hope next year we'll have some new PhD students. But the problem is that it is difficult to find clever people for this work, and to write next PhD dissertation is not what I would like to do. And area of interest of our group: phase singularities in metrology. This is a part.
Excuse me. With accreditation, yes. Is it only the problem of your group, or in general, just physics?
This is very general problem.
Okay.
Okay. Phase singularities in metrology. Optical vortices in microscopy belongs to this field. The polarization singularities in metrology, optical tweezers, fine structures of light, beam shaping, telecommunication based on optical vortices. And these all topics are bounded, so actually, to some extension, this classification is artificial. Optical vortices in brief. Optical vortices are features or creatures in complex scalar fields. Their characteristic feature is that, as you can see here, they possess a helical wavefront. And here we have some standard equations describing, one moment, please. I should take maybe, okay, this is okay. This is the most basic mathematical form describing such a beams. And actually, the most important part is this phase term. Of course, the expression is written in cylindrical coordinates. Along the central line of the helix, the phase is ill-defined, which is well seen in the cross-section. Here we have a cross-section, XY cross-section. And as you can see, the equiphase lines plotted in different colors converge to some point. This is this singular point. And going round, the phase changes by 2 pi or 2 pi multiplied by any integer. This is also possible. Here are some other plots. We have a single vortex which can be rotating in clockwise and anti-clockwise. As well, we have so-called higher order vortices, which in fact are unstable and split into single one under very small phase or amplitude perturbation.
Even in vacuum?
I beg your pardon?
Even in vacuum, they do split?
Actually, when we have well-defined vortex at the input plane and vacuum, they doesn't split.
That's right.
There must be something to disturb the phase or amplitude part.
Okay.
But usually we work in error. Okay. The light intensity is 0 at singular point. Some people call optical vortices donut beams. Optical vortices are generic and stable features within the wavefield. The other stable phase singularities is edge dislocation, but I'm not going to tell more about it. I will concentrate on optical vortices. What means generic? It means actually that it is very easy to generate wavefront with optical vortices. And on the contrary, it is very hard to generate wavefront free of vortices. And stable means that under small disturbance, they survive. As this basic optical vortices, because as I said, higher order vortices split into single one. The good example of this generic feature of optical vortices is speckle pattern. Speckle pattern is always present in laser illumination. It's a matter of rich interference between different parts of the beam, and every dark point here contains single optical vortex. So speckle patterns is just a very rich net of optical vortices. Of course, this is a characteristic feature for scalar wavefields, as I said. So we can find it in various wavefields. Here is a nice example from acoustic microscope, when we can see in phase picture two vortices. But I will concentrate on optical vortices. The other feature is that such a rotating beam possesses non-zero angular momentum, which is related to its wavefront geometry. And generally, the angular momentum of light beam has two components, polarization and orbital. By analogy to orbital angular momentum of Earth or electron, we say that the light has orbital angular momentum as well. And here is a proof that it works. We have a small bead, polystyrene bead covered by thin silver layer. And this bead is illuminated by vortex beam from bottom. And this light reflects from the metallized surface and transfer angular momentum to this small bead. And as you can see, it can easily rotate. When we change so-called topological charge of optical vortices, we can change the rotation from clockwise to anti-clockwise or vice versa. This experiment has been performed in our optical tweezers lab using the holographic optical tweezer. Here is another example. In this experiment, we used two beams. The first beam catch this central bead. These beads are transparent now, and formed a kind of axis of rotation. And here, this off-site two beads were catched by optical vortex. And as you can see, the whole device can rotate by angular momentum transfer. I have choose this picture because this so-called micro tool was developed in Warsaw in your institute or your department by a group of Professor Piotr Wasilczyk. So we have some cooperation concerning the optical tweezers. Okay, now let's concentrate on optical vortices in microscope, which is the main topic of my speech. First question is why to do, or why to apply optical vortices in microscope? There are two answers on this question. First is that the classical microscopy suffers dramatic resolution limit. Here is a picture from a Nobel presentation by Stefan Hell in 1918. That was the Nobel Prize in Chemistry for single molecule microscopy, actually. As you can see, the optical microscopes have some limits in resolution, which are very, very uncomfortable for present medicine, biomedicine, and technology. So people working or have produced many kinds of different microscopes, also non-optical, but all of them suffer some serious disadvantages. And nice optical microscope working in far distance and in air with low light intensity would be highly welcome. Still, this is an opinion from people working in technology and microscopy market. This is my first reason. It's still open game. The second reason is that some people just believe that applying vortices to microscopy must be possible. I mean, people working in singular optics. More of them say that this is a crazy idea. Okay, I think that it is nice to make at least one crazy project, if it's possible. And this is the second reason. The first project showing that we can think about optical vortices as an imaging device in microscopy was the super resolution phase image microscope, concept given by Yuri Kravtsov from Russia, realization Vladimir Tyshinsky from Moscow, also Russia. The idea was quite simple. Mainly when light, laser light, high, strongly focused laser light reflects from the sample, we have such a speckle pattern, and this speckle pattern consists a lot of optical vortices and also edge dislocation, but I am not dealing with edge dislocation now. So by magnifying the picture and investigate this phase structure in interferometric system, here is an interferometric system, we can try to relate the substrate geometry, surface geometry of our sample with this cloud of phase singularities. There is a theory saying that it is possible. And as I know, there was at least 2 attempts to introduce SUPHIM to market. So that was a very serious approach. One was by Philips Center for Manufacturing Technology. After some time, the project was shifted to separate company, NanoFocus. And the second was by Japanese company. I don't remember the name. I lost this information. Although the system was built and tested, the full project failed. The question is why? Well, the most simple answer I can give here, is that this cloud of vortices was definitely too sensitive. Any small changes in air, in environment, make that this picture just dramatically change, and there was no way to control it. So this very high sensitive was the main problem of the SUPHIM project collapse. But the race has been started. Here I list at least 3 other solutions that has been proposed from that time. There are some more of them, but I have no time to focus on it. I just want to say you that I'm not only one working in this direction. My concept was different. Instead of catching this crazy dance of vortices created by scattering from sample, I have proposed to introduce the well-defined vortex into illuminating laser beam. So then this this beam with vortex was focused on the sample, and the image was analyzed into interferometric system. Here, vortex, which has very well-defined point, this singular point, is just a phase marker, and this phase marker is sensitive on the details on sample. That was the hope that we can use it for microscopic imaging. Okay. Unfortunately, when you have some brilliant idea, you will find very fast that someone else had it before, a bit before, and that was happened in my case also. So shortly after, I have realized that the same concept was published by Boris Spector and his team. Here are 3 publications on this topic. But in my opinion, they have tried to follow the procedures developed for scanning microscopy working with standard Gaussian laser beam. The better way is trying to make a usage of specific property of the optical vortices. So we had the same idea, but different strategy for its realization. Okay, looking for this new way of using the vortices in microscope is quite difficult task, just because you still have in mind the old solutions, which push you think in old way. That's why our project goes like sinusoids. There is a progress when we have some new concept, and that time in between. But actually, because this is such a not mainstream for our works in Polytechnic, I'm not in hurry. It is nice to have a project that you don't have to be in for a hurry. So 4 years after publishing this picture, I have published. So years after I have published this picture, shown here below, we have started to work on seriously. Okay, the input was from Brussels. Some people in Free University of Brussels has asked us if the vortices can be used for inspecting such a different matrix of strange matrix of pillars or wells. Here we have well, which is very deep, comparing to its diameter. Okay? So we need a system with a strong, deep, large depth of focus, or large depth of focus, which is not very easy. The second problem is that we have a matrix of such wells or pillars. And I have tried to solve this problem using vortices. And the question was, if the side of this well or pillars are perpendicular to the base. That means that this part is correct. That means that this part is incorrect. So the task was to distinguish between this case and this case. And I have solved the analytical problem for this task using Fresnel diffraction integrals. I have solved Fresnel diffraction problem for this task in simplified version. So I asked what will happen when the focus beam, vortex focus beam, will cross the deep phase step. Okay? And the analytical answer was quite interesting. When we approach to the step, the vortex divides into two, having the same topological charge. And when we go out, it's not rejoining, but we have, after some distance, again, single vortex. When we have a slope, here the slope is plotted in gray. Okay, so when we approach to the slope, there are many vortices which dance in a chaotic way. And after some distance, we just recover the single one. So there is a definitely difference between a well-defined wall and slope.
And what happens with the charge, with the topological charge at this situation?
Yes, okay. The problem is that we observe the central part of the beam. Okay? Farther from the center, there is always a crazy game between vortices. So the question of topological charge is a question of the whole pattern. And in this in this solution, we are not interested what is going in the whole field, which would be very difficult to study. We have concentrated on the central part.
Mm-hmm.
So the question of conserving topological charge actually is not a question for the system. But generally, you are right.
Because you are looking at the subgroup, at the subsystem.
Yeah. And there is a there is a part which is coming through and reflects. So when you want to say about topological charge, we must take into account all of these parts, which is much more complicated task.
Mm-hmm.
So we have construct a simple interferometric system. There is a vortex generator. Where is it? Here is hard vortex generator, and try to check if we can use this simplified. Analytical results are always simplified to make some real system. We have used actually two vortex generator. The one was fabricated for us in United States. It's a kind of phase structure, diffraction optical element, which joins two actions. First action is a lens. In this case, is Fresnel's lens. And the second action is such a spiral faceplate, which is also called sometimes vortex lens, which introduce to the laser beam optical vortex. Okay? And we can join these two elements into a single one, which is very comfortable because having one single thin glass plate is better than having two separate elements. And the other way for doing this was applying so-called spatial light modulators, which is very modern currently in optics and photonics, and just to generate in holographic way, to display a holographic pattern, and in first order beam or minus first order beam, we have an optical vortex. Okay. Both approaches were successful, and here is a sample results. We have an interferogram recorded in our system, and such a abrupted fringe or fork-like fringe means that there is an optical vortex here. This picture was taken apart from the edge, and here we have two vortices, two forks. So we are over the edge. Now, of course, going apart, we still have some single fork somewhere here. And when there is a slope, so there is a lot of vortices being on the slope, even here, 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 here. And they, when you move a bit over the slope, they just make some crazy dance. The nice thing of this solution was that it can be easily computerized. It is enough to plot such a parallel lines and to count the fringes. When you have one extra fringes between neighboring lines, it means that there is a vortex. Sorry. The project was, although the whole idea was successfully tested, the project was stopped because, Russell partner has stopped it. I don't know what was the reason, but maybe they have no funds to continue it. But generally, they informed us that this way is closed. But we have tried to go deeper and ask if a vortex having topological charge 2 can be used for metrology. Again, I have solved some diffraction problem, and well, the formulas usually are very unpleasant, but after some studying it, we can find at least some nice illustration. And this rather complicated formula can be actually split into two plots. One plot is such a set of circles, and the second plot is a set of ellipses. And when we go over the phase step, these circles stay in place and ellipses move from left to right. Okay, when we have the same amplitude, but the different phases representing on the ellipses and surface, we have a vortex. So by moving, the vortex change their position, the two vortices. As I said, higher order vortex is unstable. They split into two. And they relatively change their position. What was very interesting, we have proof that being exactly on the edge with the center of our beam means that the vortices are closest. The distance between is smallest, locally, of course. So let's see it on the trajectory. Here is a theoretically calculated trajectory. We are approaching the edge. The vortices splits, and we are exactly over the edge with the beam center. The distance between them is locally minimal. And after going further, they are farther and farther, and after some distance, rejoin. So this minimum of distance is local. Experimentally, it looks worse, but still, we have some closest, smallest distance between vortices, which means that we are over the edge. And we are able to show that we can measure the edge position with a resolution of 60 nanometer, which is far below the resolution limit. We use a lens with aperture, numerical aperture smaller than 1/10. It's actually a very weak lens. But after that, I've tried to calculate more complicated problems. And the formula was so complicated that we were not able to analyze it reasonably. Mainly, I have tried to find what about vortices with topological charge 3, 4, and so on. Or try to calculate, for example, how it behaves when we have two very close each other phase steps. It was very, very difficult to find reasonable analysis of the results. So there was a small break in our project up to new idea, internal scanning method. Internal scanning method is very simple. You just move the vortex generator. For example, the spiral phase plate. Now we mostly use spiral phase plate. When you move it, you may expect that vortex point, this singular point, will also move. And the full focus spot will stay in place. And here is exactly what it happened. We move this spiral phase plate perpendicular to the incoming laser beam. And in result, the vortex point moved, but the full beam stayed in place. So the idea was to try to scan the sample just with this dark point. The nice thing is that when the beam is focused, its diameter is smaller. So it means that when we, for example, move a spiral faceplate by 1 millimeter, so the vortex inside the focus beam will move 100 times at 100 times smaller range, or 1,000 times smaller range, or so on. And at least we have here a very stable system for scanning without a problem that we usually meet when we want to scan with nanometer resolution. Because reducing the range 400 times, okay, when I move my system by say 400 nanometers, which can be down in a very stable way, the vortex point will move by 1 nanometer. Okay? And it will be still resistant from thermal and mechanical vibrations on which all these difficulties which have nanometer microscopic tables with nanometer resolution. We have solved a problem, the following problem. Analytically, what is exactly the trajectory of optical vortex point, this dark point, when you move the spiral faceplate? First, we have these are really difficult integrals, there's longer story, but we were able at first to solve it for small shifts. That means this SPP spiral faceplate shift was small, and find a trajectory of optical vortices analytically. Okay, they were a bit surprising. We have found that this trajectory rotates. So, for example, when you move the spiral faceplate along X-way, the observed vortex trajectory is at different angle. And this angle rotates towards the focal point. When you are at focal point, it's not exactly focal point, but very close. We prefer it, say, for short, critical plane, critical position. The vortex trajectory is perpendicular to the spiral faceplate trajectory. Here we have some analytical resolution for angle of orientation of this vortex trajectory. Some plots, as you can see, the most of the rotation take place in the small neighborhood of this critical plane. So first, the rotation is very slow, and then the rotation is very rapid, which is well seen on this plot of derivatives of angle. We have a bit reconstructed our system because of different reasons. Decided to work in Mach-Zender interferometer as before, but with carrier frequency methodology. That means that we have registered such a fringes with quite dense fringes, then to analyze it by Fourier transform, move the coordinate system to the first order or second minus first order beam, and perform the inverse Fourier transform locally to get rid of this carrier frequency. This effectively allows us in a very fast way and quite accurate to reconstruct both the amplitude and the phase of the beam. And when you have a new system, you have to test it, and there is a number of tests performed on the system. We have found that it works quite nice. Okay. Here is an example of such a test. There is an optical wedge, and we move this wedge perpendicular to the beam. And while it is moving, okay, what we expect is that the optical vortex is rotating, as you can see. The wedge was 90 seconds, It means that we need to move it by 2.5 millimeters to acquire 2 pi phase shift, but everything works properly. What was surprising in very simple experiment, just without no intention, we got such nice phase sensitivity. We could distinguish between rotation causing phase shift by lambda over 50. Okay. And another test, how it behaves. We move the vortex length, causing moving this dark point in sample plane. It's strongly focused now. And here you have a typical trajectory without a sample. When you put a sample, for example, a row, a phase row, this trajectory has definitely different geometry. So it's sensitive for such problems. Okay, the biggest problem in any non-classical optical system is to construct the procedures for analyzing images. You get some different information we are usually not used to, and we need to find a theory which will relate these results to, for example, sample topography, which is usually the most difficult task. It doesn't matter if we have, for example, optical tomography or IFM microscopy. This is always the main problem. And to solve this, it's nice to have a full analytical model instead of an approximate one. So we try to do it, solving this diffraction problem in a more complex way and without approximations. We divide our system into 3 subsystems: vortex unit, sample plane, magnifying unit. So we have 3 steps describing light propagation from vortex unit to sample plane, from sample plane to magnifying unit, from magnifying unit to observation plane. The solution of our basic integral from vortex unit to sample plane is maybe not nice, but works quite effectively. And what is more important, we have shown that any next step in our system, whatever number of this step is, can be described in terms of this function g. The only difference is in coefficients. And we have also derived the formulas for these coefficients for any number of steps. So this is nice part of the solution, because it means that propagation through our system is invariant in the context of this function g. So this is an example of coefficients after the second steps from sample plane to magnifying unit. After the third step, here we could plane another objective and go farther, go farther, go farther. And what was also nice, actually these formulas describe what is going on around the central part of the vortex. And we actually analyze the vortex position and the so-called vortex core, which is just the central part of the vortex. This donut beam is just described by the term with n. It is mistaken, n equal to 0. It's very simple formulas. And it describes the movement on the vortex and the phase geometry of the vortex core very effective, which is really nice things. Here's a comparison. What we can get when you put n equals 0 and equal 63. This is this main part of expansion. Here we have n, the main sum. And numerical simulations based on independent algorithms. Oh, it works quite well. This very simple approximation to n equals 0. And the experiment shows very nice agreement between theory and practice. Here we measure the angle of rotation of the vortex path trajectory. dots are angle theory, crosses are experiment. And here we have measured the range of the or maybe reduction of the trajectory. For example, when you move the vortex length, as I said, the vortex length by, let's say, 1 millimeter, the vortex trajectory at focal plane reduce 100 times, 200 times, depends on optical system. And this reduction was exactly the same as in theory. After that, I have analyzed some symmetry of all this term in this sum and found that there is a true symmetry in it. And we were able to describe the whole expression in the terms of special Kummer confluent hypergeometric function without these infinite sums. And what is important, this is for any order of vortex. So we may describe not only the vortex with a single charge, but also with any integer topological charge. That's why the formulas are split into odd and even case. Okay, the conclusions from this experiment were very interesting, at least for people working in this field. Mainly the coefficient A plays the same role as the GOI phase in the theory of Gaussian beams. The higher order vortices does not split regardless the number of elements used in our system and the value of X. This is very interesting and surprising solution. Because, as I said, the vortex is very sensitive, higher order vortex is very sensitive for any phase and amplitude disturbance. And this is very special case that this is not true. It doesn't split. And our numerical calculations confirms this. Also, some other much more partial results obtained by other people confirms that it must be in this way. And the vortex trajectory behaves like a 3D body while rotating. Okay. Now, we have also developed first global procedure for image recovery. The one way is to analyze the vortex trajectory, and the other way is to try to analyze the full vortex core in order to get the image. And here we have some initial interferometer structure obtained by our system. And we have tried to analyze such a square groove in glass, very small. And after some processing and the final image. There is some processing, of course, of this start image, and then the groove geometry. The same down in standard scanning optical microscope gives no image. More important is that we could do it also for two closed grooves to see it as separate. But I realized that these procedures are very simple and primitive still, because as I said, it's very hard. This is the most difficult task always when you are developing a new non-classical device to define such a procedures. And we can use OVSM, Optical Vortex ScanningMicroscope, as interferometer. It has really good sensitivity, very high. And shortly saying is why. Usually in standard interferometer, we have a number of fringe to be able to reconstruct the phase. Here we have actually used only one fringe, which is folded. This is our one fringe. Okay? So we have more space on camera for single fringe. Okay? Actually, registering single fringe in standard interferometry covers the full camera, but it's not enough to reconstruct the phase. And we can use, first, we can use only one fringe. And secondly, because it is folded, so it is 2 pi multiplied by radius. So the path we can analyze the phase along this fringe is much longer than in case of single fringe in classical interferometer. We have tried to measure this phase, and so far, at first, we stopped at accuracy lambda over 120, not because it was the final possibility in our system, but because going further means that we had problem with system stability, mainly error and table vibration. 100, I'm very close to end. Yes. Next step was applying neural networks to successfully find the vortex position. This is very important task also, to find exactly a vortex position. By neural networks, we could make it almost 3 times better than in with old methods. I have little idea about neural networks, but people who work on it said that it was very difficult to learn this network, to make a task. But finally, when they did it, the results are very nice. First, neural networks make it very fast, and secondly, very accurate. We have some special procedures to check the accuracy, and actually have no doubts that we can measure the position of vortex with sub-pixel resolution. Pixel, I mean here, pixel on camera. And here is the place we are with our vortex project, roughly saying, because there are more technical details in more different partial achievements. And what next? First, we need we want to find analytical description, including finite aperture. Secondly, we are working on testing the project, the new procedures for image recovery. Thirdly, we want to apply neural networks for testing vortex score. And at 4 point, new geometry of the optical vortex. We want to use new geometry of the optical vortex, so-called composed vortex, which can be more useful for our task than the standard classical vortex. So we still don't have optical vortex scanning microscope. It's still under development. But what I can say, this project supports us with quite nice technology, or teach us how to use vortices for different tasks, and how to use spatial light modulators. And that was used for all these other fields of interest I listed before, including, for example, holographic optical tweezers. Without this knowledge, it will be much harder to open these new areas. So anyway, although still without final success, I consider this project for my group as truly successful because of this off-site effects. Okay, thank you for your attention.
Okay, thank you very much for a very nice and interesting lecture.